Let's take up reversible process. This process is slow and unreal. Its direction can be changed at any step. By this, the maximum work done by the system can be obtained. This is the diagram where we are showing you reversible process. Now, reversible process in thermodynamics is slightly different. This is the initial state where you find piston is here. And we are releasing the pressure. Our piston has moved to this position. So we have got now volume has increased. Now there is maximum volume because pressure is minimum. We are again applying pressure, and when we again apply pressure, so what we find is that we have got second stage again, that is initial process, second stage of the initial process we have got. Here we are applying pressure, and if we apply a pressure more, we get the initial process back, first stage of initial process back by applying pressure. So this is the called restoring process, this is initial process, and this thermodynamic process is called reversible process. Next we are taking irreversible process. The irreversible process is fast. Reversible process was slow, whereas irreversible process is fast. And all the natural processes are of this type. In this, the work done is less than that in the reversible process. W irreversible will be less than W reversible. Now we are taking thermodynamic equilibrium. Now whenever we have reversible process, we also have equilibrium. What do you mean by equilibrium? Equilibrium means that rate of forward process and rate of backward process becomes equal. That is called equilibrium. And when there is equilibrium between the energy changes, then we call it thermodynamic equilibrium. When macro properties of the system do not change with time, the system is said to be in equilibrium. Now, after the equilibrium is reached, the macro properties of the system becomes constant. And if we change the macro properties, then new equilibrium will reach. So when particular equilibrium reaches, its macro properties do not change, pressure, temperature, concentration, color, everything becomes constant. Next, we are taking mechanical equilibrium. When no work is done by one part of the system on the other part, it is said to be in state of mechanical equilibrium. Now, equilibrium is the stage of stability. So, mechanical equilibrium also leads to stability. Pressure remains constant throughout the system in mechanical equilibrium. Thermal equilibrium. In thermal equilibrium, temperature remains constant throughout the system. Just like in mechanical equilibrium, pressure remains constant. In thermal equilibrium, the temperature remains constant throughout the system. When temperature remains constant, so no transfer of heat can take place from one part of the system to another. Chemical equilibrium is very important, and our next chapter will be chemical equilibrium. In chemical equilibrium, the rate of forward reaction is equal to rate of backward reaction. The stage at which the rate of forward process and backward process are equal, they are in chemical reaction, it is called chemical equilibrium. And in this, composition of the system remains constant and definite. Means molar concentration remains constant, temperature, pressure, color, everything remains constant in the chemical equilibrium. Now we are going to take up internal energy. The fixed amount of energy contained in a substance is called internal energy. Now, internal energy has many components. The first component is internal energy is due to translational motion of molecules. Second component is it is due to rotational motion of molecules. The third component it is due to revolving or motion of vibrational motion of molecules. Vibrational motion, rotational motion and translational motion of molecules. There are 3 points of internal energy. Another is internal energy is also due to bond energy. Bond energy means energy required to break the bond. Is called bond dissociation energy, and energy released in formation of bond is called bond energy. Another component is the force of attraction between valence electron and nucleus. So that is also responsible for internal energy. And intermolecular, sixth component is intermolecular force of attraction. That the force of attraction between the molecules is also responsible for internal energy. So I have given you 6 components which constitute internal energy. Internal energy is present in all the substances. For example, the energy required to break a chalk depends upon its internal energy, and you know its internal energy is low. But if we want to break a pen, you need higher energy. It means internal energy of pen is higher than the chalk. Quantitative properties. Internal energy depends upon chemical nature, pressure, temperature, and volume of substance. These are the quantitative properties which determine internal energy. State functions. Internal energy depends upon physical state of the system, therefore it is called state function. Internal energy is the total of all types of energy which I have taken earlier also: potential energy, kinetic energy, vibrational energy, rotational energy, etc. Sixth, now absolute value of internal energy cannot be calculated except for ideal gases. For ideal gases, U will be equal to 3 by 2 RT, and but delta U will be equal to 0. For them, we cannot find out delta U, although absolute value we can find out for ideal monoatomic gases. Change in internal energy is most important, in which we are interested. And what is change in internal energy? This is energy in final state minus energy in initial state. That is, delta U is equal to U2 minus U1. So delta U is energy of products minus energy of reactant. This is very important. We can also say sigma of energy of products means sum of the energy of products minus sum of the energy of reactants. Even we have to multiply them with their coefficients also to get the value of delta U. Internal energy is an extensive property. Extensive property means it depends upon amount of substance. In most stable form, internal energy of the system is regarded as zero. As I have told you that internal energy of 1 mole of monoatomic gas at temperature T Kelvin is equal to 3 by 2 RT. This is for 1 mole, and if we have n moles, so it will become 3 by 2 nRT. Here delta U is positive in endothermic process and delta U is negative in exothermic process, and we know that delta U is equal to Q plus W. Now internal energy is 3 by 2 RT and enthalpy, that is denoted by H, is equal to 5 by 2 RT. Why? Because H is equal to E plus PV and PV is equal to RT. So 3 by 2 RT plus RT will become 5 by 2 RT. So enthalpy of 1 mole of monoatomic gas at T Kelvin will be equal to 5 by 2 RT. Let's take our first law of thermodynamics. Energy can neither be produced, that is created, nor destroyed. It can be changed from one form to another. The total energy of an isolated system remains constant, and total energy of universe also remains constant. This we have shown with the help of diagram. This is the initial state and where internal energy is U1. This is the final state where internal energy is U2, and U2 minus U1 is delta U, that is change in internal energy. We are exchanging heat transfer is done by Q, means it will be given to the system or it will be taken out from the system. So we call it heat transfer instead of heat absorbed or evolved. Similarly, work done may be on the system or by the system. So according to first law of thermodynamics, delta U, which is equal to U2 minus U1, should be equal to Q plus W. So this we have shown from one state to another state, internal energy change will be equal to Q plus W. Whenever some amount of energy disappears, the same amount of energy of other form is produced, and that shows that the energy remains conserved. Mathematical form, delta U is equal to Q plus W. Let us discuss the various cases. For isothermal process, energy change in the system is equal to heat given to the system plus work done on the system. Now in case of isothermal process, if you remember, delta T is 0, so delta U becomes 0. Now if we keep the delta U 0, then it will be 0 is equal to Q plus W, that is Q is equal to minus W. Means heat absorbed by the system is spent in doing work by the system. For isochoric process, isochoric means there is no change in volume, and if there is no change in volume, then P delta V will be equal to 0. If P delta V is 0, W is equal to 0. And W is 0 means system does not do any work. So the expression delta U is equal to Q plus W becomes delta U is equal to Q plus 0. Heat given to the system at constant volume changes the internal energy. I can also define it like this, that internal energy change is equal to heat exchange with the surroundings at constant volume. That is, constant volume means that the process is carried out in closed container. For adiabatic process, if you remember that Q is equal to 0, means no heat is exchanged with the surroundings. So delta U will be equal to 0 plus W. That is, delta U is equal to W, means work done on the system changes the internal energy. Another point, when a gas expands against a constant pressure P, then the work done will be equal to minus P delta V. This P is external pressure and delta V is change in volume, and change in volume is equal to V2 minus V1. So we can modify the equation delta U is equal to Q minus P delta V. Now W is in liter atmosphere. If it is in liter atmosphere, we can convert it into joules. 1 liter atmosphere will be equal to 101.3 joules. Now, if the gas expands in vacuum, vacuum means external pressure is 0, then work done will be equal to 0. And this can be also called free expansion. Why free expansion? Because no pressure is acting on the system. And if pressure is not acting on the system, and because as it is vacuum, so the free expansion of the gas will take place and work done will be 0.